You can't.
Okay, so we're doing statistics today.
Mm-hmm.
Are you taking these with a camera, a smartphone camera?
These were on my iPod.
These are from your iPod.
Mm-hmm.
Is there any way that you have another camera? The last couple times I've had a real hard time reading them, as you can tell. I can barely make this out. If there's another camera that produces a little bit better quality, a little higher resolution, maybe your mom's smartphone camera. Almost any smartphone has at least 4 megapixel. This looks like it was taken at about 2 megapixel.
Oh, my iPod's better than my mom's, but maybe I just took it blurry. Do you want me to?
No, we can make through this. You may have to read some stuff to me, but you can see that it's hard to read.
Okay.
I don't remember last year, if your mom was taking them, those were legible. So maybe you don't have it set on the highest resolution on your camera. I don't know. Or need to stabilize it a little bit better or something. A lot of times it really matters if, I know I take a lot of pictures and move that math stuff to my computer, and boy, sometimes I can keep my hand steady, sometimes I don't. It really makes a difference. All right, let's talk about standard deviation and average values and normal distributions. Have you talked about normal distributions? This curve I've drawn here is a normal distribution.
I don't know if we have. I don't think so.
Well, let's not get into that then. It's statistics is something that they're working more and more into the Common Core, much to my chagrin, because I don't tutor probability and statistics, although this is very basic stuff here. The mean is the average number. You know how to get the average number. How would you get it? If I gave you this list of numbers and said calculate what the average is.
You'd add them all up and divide by 6.
Right. And when you do that, you get 15. So when they give you a list of numbers and they give you the average, and then this sigma here, standard deviation, equals 3.9, is a measurement of how much of the data and how far it is away from that average. So let's look at question A. What's the lowest point that could still be only 1 standard deviation away from the mean? And then they tell you how to do it. In other words, start with the mean and subtract the standard deviation. So what would you get?
Okay, so do 15 minus 3.9. 11.1.
Okay. So 11.1 is 1 standard deviation away from the mean. So what is the lowest number? What's the lowest data point that can still be only 1 standard deviation from the mean? Would it be 10 or 12?
12.
12, yeah. In other words, 12 is inside that. In other words, if you take the difference between 12 and 15, it's 3, while standard deviation is 3.9. So I can go as far away from 15, I can go 3.9 away, either side. Okay, so 12 is the lowest number that is within 1 standard deviation. And B says, what's the highest data point that works? So what's 1 standard deviation above 15?
16.
take the mean and add 1 standard deviation to it, just like we took the mean and subtracted 1 standard deviation in the other direction.
18.9.
So, any number that is between 11.1 and 18.9 is within 1 standard deviation of the mean. So, what's the highest data point that works?
In between those two numbers?
Yeah.
18.8.
Well, that's not in our list. So, from the list of data points, what's the one?
Oh.
Which, just like 12 was the lowest, what's the highest?
15.
Yeah, the actual mean. In other words, 19 is not within 1 standard deviation of 15. So the answer would be 15. So the answer to A is 12, and the answer to B is 15.
All right.
What of the original data set are within 1 standard deviation of the mean? In other words, which of the data are between your 2 answers? So if you answer the question, which of our data points are within 1 standard deviation of the mean? What's the answer?
Um, 15.
We have our mean, we have our standard deviation. Anything that is between 1 standard deviation less than our mean and 1 standard deviation above our mean fits our criterion. So there's the low end, there's the high end. Which numbers are in between those? Which numbers from
12,
our
13, and 15.
Yeah, exactly. From our data set, which numbers from our data set are in between that? So that's the answer to C.
Is 12, 13, and 15.
Uh-huh.
Okay.
It tells you, in other words, which of the data are between your 2 answers, A and B. Well, this was A, and this was B. They should have said including your 2 answers, because 12 and 15 were our answers. But 13 is also within. Understand what the concept means. Standard deviation is merely a distance to the left and a distance to the right. All right. What percent of the data points are within 1 standard deviation of the mean? This is something that you just have to memorize. Let me write down the answer for you. There's no way to figure this out. This is just the case. 68% is within 1 standard deviation. 95% is within 2 standard deviations, and 99.7% are within 3 standard deviations. And this question suggests to me that you have had normal distribution, because otherwise this wouldn't have much meaning. This is a very small string of data. That's only 6 data points. So it doesn't make a whole lot of sense, these 3 questions here. But, you'll notice that only half of the data points were within 1 standard deviation of the mean.
Yeah.
Well, that's close to 68%. If we had a longer list of numbers, we'd probably have a chance of being closer to the 68%. But they're saying that overall, with a normal distribution and a large set of data points, you will find 68% of them are within one standard deviation. Furthermore, you'll find 95% of them are within two. Well, two standard deviations here is 7.8, and if you add or subtract 7.8 from 15, you find out that all 6 of these data points are within 2 standard deviations of the mean. So from our list, this came out to be 50%, but this came out to be 100%, and of course, within 3 standard deviations, 100%. But like I said, if you had a very large list of numbers, or say heights of people in the United States, let's talk about that, because this is a normal distribution. We have our adults. We'll say heights of adults. There's 4 foot tall. There's 5 foot tall, there's 6 foot tall, and there's 7 foot tall. If you were to get a list of the heights of all adults in the United States, which would be like 200 million heights, you would see that it very much looks like a normal distribution. That's what a normal distribution looks like. Meaning most people are going to be between 5 and 6 foot tall. But a smaller percentage of the people, on this axis here, this is the number of people at that height. Okay, so the most number of people are going to be at this height here. Well, let's say I said the mean height of all 200 million adults was, counting men and women, we'll say 5.5 feet high. And there is a standard deviation, I'm just going to make this up, but we'll say one standard deviation is 1 foot. Now, let's say 6 inches. Now, when I wrote those percentages there, here's what this means. If I go 1 standard deviation to the left from 5.5 feet, I'm at 5 feet. If I go 1 standard deviation to the right, I'm at 6 feet. I'm going to go 6 inches left, 6 inches right. So what it's saying is that the area under the normal distribution curve is 68% of the total area under that curve. That's what statistics, standard deviation, and mean are all about. If I said, well, how about 2 standard deviations? Well, 2 standard deviations is 1 foot. So 2 standard deviations goes out to here on the left side and to here on the right side. So now we're talking about everybody in the United States that is between 4.5 and 6.5 feet. What statistics tells us is that that's 95% of the people. 1 standard deviation was 68% of the people would be within 5 feet and 6 feet. 2 standard deviations, 95% of the people are going to be this way. And if you go 3 standard deviations, which would go 1.5 feet in each direction, which would mean you'd be going from the 4 foot high adults to the 7-foot high adults. 99.7% of the people, the adults in the country, are going to fit in between those two numbers in terms of their height. The height is the x-axis and the vertical axis is the number of people that are in that category. In other words, the most amount of people are going to be right here at 5.5 feet tall, within a very narrow.
Okay.
They're within a very narrow range. You can't really say that the median, which is the most common, no, excuse me, you can't really say that the middle is 5.5 feet. That's the median. But the mean, if you took everybody's height and divided it by the number of people, you would get 5.5 feet is the average height in the United States. But it's quite useful from a statistics point of view to know what the spread is. In other words, it means something different altogether if I say the average is 5.5 feet and the span is from 4 to 7 feet than if I say the average is 5.5 feet and the span is from 1 foot to 10 foot. In other words, if I were to draw a normal distribution curve that is flatter, and it really does go from 1 foot to 10 foot, and the average is 5.5 foot, well, this might represent some sort of model of data, but it's not going to represent the height of people. And this model would have a greater standard deviation. The standard deviation on that model might be 1 foot instead of 6 inches. So standard deviation is kind of a measurement of the range of the data and the distribution of the data. Notice that if my low point was 1 or 2, and my high point was 50 or 60, those would be outside of 3 standard deviations even. So a lot of data in real life can be represented with what is called this normal distribution. And it can have various shapes. Usually it looks like the one on the right. Sometimes it can be a little flatter or a little skinnier in the middle, but all of them have this concept of standard deviation involved. And these 3 numbers are important to remember. Whatever your standard deviation is, usually 68% of the area under the curve, which was in my example the number of people, will be within 1 standard deviation of the mean. And 95% will be within 2, and 99.7% will be within 3.
Okay, so D would be like 50% since
Yes,
it's
exactly.
half of it.
Yes, so D is 50%. Let's go on. Outliers are data points that are not typical in the sense that they are, what's that word, way bigger or way smaller than typical data points. In other words, in our previous set of data points, we didn't have any outliers. Everything was within 2 standard deviations of the mean. So here's a new data set. Oh, I see. Outliers, in other words, there are more outliers lie more than, what does that say? 1.5 times what?
IQR.
What's IQR?
I think it's the something range that
From the nearest quartile. I don't know what those words mean.
I think it's the interquartile range.
Like I said, I don't know what the word quartile means. I have an Algebra 2 book here, and it doesn't mention those words. So your teacher is using terminology that a statistician might understand, but I don't. And nowhere in my Algebra 2 book does it mention those words. So you're going to have to tell me what they mean.
I don't know either, so... Oh wait, yeah, I do.
Okay.
You know how there you find the median?
Yep.
And, and then, like, the quartile 1 would be... I don't know how to explain it. It would be, like, from the first point to the median, like, you know, in order, what those numbers median would be.
Can you give me well, can you work this problem? Here's the data. Outliers lie 1.5 times this IQR from the nearest quartile. And consider this data set. Calculate Q something, and IQR. So if we can do this problem, I'll probably understand what IQR means and the nearest quartile. The nearest quartile, does that mean the nearest fourth?
No, it's like you you subtract quartile 1 from quartile 3.
Okay, I don't know what that word means, so it means nothing to me when you say subtract quartile 1 from quartile 3. I don't know what a quartile is.
Okay, do you want me to give you an example so
Yeah.
you do know what it is? Okay.
Well, can you give me the example with this data set? Because that's what they're asking. They're going to ask us 5 questions here about quartiles.
Okay, well, you'd have to find the median, and the median is 203. And then you...
Okay, so the median is 203. That's the middle.
And then you have to find the medium of the numbers before the median.
Are you saying medium?
Yeah, like the number in the middle.
Well, that's the median. It's spelled median, like that.
Oh.
It's not
Sorry.
medium. I don't know. I wasn't sure whether I was just mishearing it or not, but it's median. Okay, so that's the middle number. Now what does the first quartile mean? Or
the first quartile is the median of the numbers before the whole data set's median.
Okay, so we're talking
so
the first fourth of the numbers, the second fourth of the numbers, the third fourth of the numbers, and the fourth fourth of the numbers. In other words, if we take our numbers and divide it up into 4 spots, or as you say, an initial median, and then a median between that, and a median over there, we'll have 4 different quartiles. Okay, I get it. So calculate, what is that little subscript? Q what? What are these two?
Q1 is...
So if you're calculating Q1 here, the median between 203 and 10 is what, 180, 190? 190 and a half. So it's all numbers less than 190 and a half? Is that the way it works? Or is it just a number?
No, it'd be, you have to find the median from numbers 10, 12, 185, 196, and 202. So it'd be 185.
So you ignore the 203?
Yeah. It's the numbers like before that, not including it.
So Q1 then is 185, right?
Mm-hmm.
It's just a specific number. And Q2 then would be 203. Is that right?
240. Oh, well, Q2 is just the medium. Like,
Right.
we
In
don't
other
call it
words,
Q2.
yeah. Okay, but that's what I'm trying to understand it myself. So, and then Q3 would
Okay.
be median between 221 and 580, which looks like 245.
Mm-hmm.
Okay. So, what does it mean? Outliers lie more than 1.5 times IQR. What is IQR?
IQR is the range of the interquartiles. So you do
So the range is
185
60.
or 245 minus 185.
Okay, so IQR equals 60. Is
Um,
that right?
Let me check.
I mean,
Yeah.
245 minus 185 is 60. Okay, so now I think I understand it. So outliers lie more than 1.5 times from the nearest quartile. So we're looking for any points that lie 90 points from the nearest quartile. Does 10 lie 90 points? Well, let's see. We've calculated all this. We've calculated that. B is 90. Subtract from Q1. So we take 185 minus 90. We get 95. So anything that's under 95 is an outlier. So 10 and 12 both are going to be outliers. It says add. Shouldn't this say add or subtract? Because outliers are at either end.
Mm-hmm.
In other words, this one says, I get it, this one says subtract, this one says add. Okay, so when you subtract 90 from, this says Q1, right?
Yeah.
Okay,
Mm-hmm.
then you get 95. So any points less, any data points lower than that are automatically outliers. So 10 and 12 are outliers. All of this stuff down here, what? Oh, this is what we're supposed to, oh, I see. So Q1, Q3, so the median minus Q1 minus Q3, okay, calculate that, subtract that, add that. Specify all outliers, if any, in the original data set. Okay, 10 is an outlier, 12
So
is an
is 12.
12 is an outlier. Now let's look in the other direction. What are we going to do to find the high-end outliers?
580 is an outlier because it's above 335.
So we're going to take Q3, add 90 to it, which is 335, and anything above that. Okay. Is there anything else we need to do with this problem? Or is that, do we have everything?
That's it.
You can get these if you have to answer these questions. We've done all of that.
Mm-hmm.
Not quite sure what this one. Why does this say IQR minus Q something else? Equals?
No, IQR equals Q3 minus Q1.
Ah, okay. Which it would. In other words, yeah, that's how we got it. Okay, I got you. All right, let's move on to the next one. Outliers can have a significant impact on the statistical makeup of data. Consider that following set of numbers, which is the set of ages of a group of 9 freshmen. Mr. Jenner, the teacher apparently, and his 4-year-old son, and his 6-year-old daughter. Okay. Make a prediction. Which of the data do you think would be outliers? If you just think about the ages of the people involved, explain.
I think it'd be 4 and 6, and then 49.
Okay. If we do a rough approximation, our Q, how many, what do we have? We have 9, 10, 11, 12 people. So 1, 2, 3, 4, 5, 6. Our median is 14 and a half. Our Q1 is 14. And our Q3 is 15. So the difference between Q3 and Q1 is only 1. 1.5 times 1 is 1.5. So anybody that is 1.5 years away from Q1 or Q3 is an outlier. And that's correct. 4 and 6 are much further away, and so is 49. Although, by this definition, if there was a 16-year-old in the group, he would actually be an outlier also. You see why?
Yeah.
Because there's not much of a spread between Q1 and Q3. Q1 and Q3 is a very small number, so even when we multiply that by 1.5, we still get a small number. So, all right. Use your GDC. What's that?
The calculator. The
Okay.
big calculator.
Oh, that's the name of your calculator?
Yeah, it's a GDC calculator.
Okay. They haven't forced you to get a graphic calculator yet? Where is that?
No, that is a graph
That's what
calculator.
the G stands for, is a graphing digital calculator or something? Okay.
Yeah.
So to calculate the following statistical measures accurate to 1 decimal place. So figure out the mean. What's the mean?
14.5.
And that was the median.
Oh. Wait, is the mean X with the line over it?
Yeah. X with the line over it is the mean, which is the average. So add up all those numbers and divide by 11. No, by 12, excuse me.
All is added up are 190. So divided by, what'd you say?
12. There's 12.
It's 15.83.
Okay. Now the next question says, what is the standard deviation? Have they given you a way to figure out standard deviation? Because so far in every problem they've given us that.
No, I don't think so.
You don't have a way to calculate standard deviation? I'm looking at a formula in my book that says standard deviation is the square root of NP times 1 minus P. But that is basing it on certain trials. My book doesn't even give me the formula for calculating standard deviation. So it seems an odd question that they're asking there. Don't know that I'm going to be able to answer that. Let's go on. Maybe we'll find out more information as we go on, and we'll be able to come back and answer that. We can certainly do Q1.
Which is 14.
And the median, Q2?
14.5.
And Q3?
15.
So IQR, or one, is that, yeah, IQR,
Mm-hmm.
which is,
1 because 15 minus 14
okay,
equals 1.
and 1.5 times IQR?
Is 1,
I'm sorry,
1.5.
I'm sorry, Q1 minus 1.5 times IQR. That's what that says. I'm having a hard time reading it.
Equals 12.5.
And Q3 plus 1.5 IQR.
16.5.
Okay. So I was wrong. A 16-year-old would not be an outlier. A 17-year-old would be. Okay. So that gives us the range. Everybody that's in that range is not an outlier. Anybody that's outside that range is an outlier.
Mm-hmm.
Which of the ages are actually outliers? According to the outlier boundaries, we've done that. Does this match your prediction from part A? Yes. If we remove the outliers from the data set, what would be the new data set? Well, that's easy. It would be all the 14 and 15-year-olds only.
Yeah.
Okay, so the only thing we have to come back to is that standard deviation question.
Actually, he said that a lot of us wouldn't know how to do that one, so he's going to explain it in class, so.
A lot of you didn't know how to do that one?
Yeah.
Okay.
And he says that he's going to explain for the next class, I guess, so.
All right. All right, let's see. We're looking at the same data set. When the outliers are removed, do you predict that the mean will go up, go down, or stay about the same? Explain why.
Sorry, I didn't hear you. What'd you say?
This question A. When the outliers are removed, would you predict that the mean will go up, down, or stay about the same?
Stay about the same.
Yeah, I would think so. In other words, when I drew my picture of the standard deviation, well, let me draw a little bit better picture over here. That's awful. Notice that according to the normal distribution, the outliers are these guys here. Okay? So it doesn't really affect this point here much at all. So I'm not sure what he wants for an explanation there, but I never am with math. You know what I mean? I mean, the reason I love math is because it's precise, all about numbers, no subjectivity to it. The moment you get somebody to try to explain something, now it's your teacher's interpretation as to whether you explained it properly. Okay, when the outliers are removed, do you predict that the standard deviation will go up, go down, or stay about the same?
We couldn't figure out the standard deviation, so.
Well, but we can say something about it. In other words, standard deviation is a measurement of how far the data is from the median. By removing these outliers, we've now got a curve that goes like this. So nobody is that far from the middle. In other words, we're going to reduce the standard deviation. It's going to go down when you remove the outliers. Notice that if I looked at just this table, 14, 14, 14, and then 5 15s, that's very little standard deviation there. If I gave you a table of numbers and everybody was 15, the the standard deviation is 0. There's no deviation from the mean in anywhere. So when you remove numbers from your data set, you have squeezed everything closer together. We no longer have much distribution in our data set. It goes from 14 to 15 and that's it. Very little standard deviation. In other words, 99 standard deviation between 14 and 15 is going to be about 3 months, because everybody fits within 3 standard deviations of the data. In other words, if we said the mean is 14.5 and standard deviation is 3 months, then I would be able to say that the entire class fits within 2 standard deviations of the mean. And that's correct. 100% of the entire class fits within 2 standard deviations. But when we had our original data set, remember these numbers that 68% are supposed to fit within 1 standard deviation. Well, 68% is just about all of the students. So the standard deviation is going to be high enough that it's going to exclude these people here and this people here. But as you think of standard deviation as not the range between the lowest and the highest, because that would be determined by outliers, and you don't want that. It's just an overall general measurement of the tightness of the numbers. That's what standard deviation is. It's a measure of that. For example, let me just see if I can get my point across a little bit more. If I took the standard deviation of those 3 numbers, 6 numbers, it's not going to be very much. It's going to be a pretty small number. But if I have the following set of numbers, they both have the same median, 14.5. But these numbers are all scrunched together. That binomial distribution kind of looks like that, with that being 14 and that being age 15. Well, if I do the normal distribution of these numbers, I get something that's far more spread out. This is 2 on the end. 22 over here, same median, 14.5, but a much bigger standard deviation because these numbers are all over the place. That's the meaning of standard deviation. And if I changed the lower data set to be this, I've just reduced my standard deviation. Notice that most of the data falls within that area there. These would be outliers. This data set is not going to have as small of a standard deviation as this one, because this one still has outliers in it, and outliers will affect your standard deviation. They definitely affect this normal distribution curve that you can draw, which you apparently haven't learned about yet. But all right. When outliers are removed, you predict that the median, the first one was the mean, and the third one, C here, is the median. Will go up, down, or stay about the same?
Stay about the same.
Yeah, it behaves much like the mean does. It's not going to change a whole lot when you remove outliers. Okay, how about the IQR? When the outliers are removed, is the IQR going to go up, down, or stay about the same?
Stay about the same.
It's going to probably go down. Think about the IQR. In my two lists of numbers here, let me get rid of all my garbage so you can tell what I'm looking at. Look at these two lists of numbers. Let me make this 29. Notice Q1 or Q3 minus Q1, which is IQR, is 1, right? For my top list?
Mm-hmm.
Well, my bottom list, this is the median, Q2. Well, Q1 is that one, I guess. But Q2 is going to be that one. So the difference, Q3 rather. So Q3 minus Q1 is 2 down here. There's a little more spread. I go from age 13 to 15. Up here, I didn't have anything below 14. And, you know, this could easily be a 6 or a 12 to add a little bit more distribution to the numbers. And then, of course, IQR gets bigger still. So IQR is a bit like standard deviation. As you introduce spread to the numbers, let's make that one 12, your IQR goes up and your standard deviation goes up.
But the IQR for problem 6 was 1 and this one's still 1.
True. But in general, this is not a good problem to demonstrate IQR will go down when you remove outliers. Well, you know what? Now that you mention it, now that I'm thinking about it, maybe you're right. It may stay about the same. Yeah, because the outliers aren't going to affect Q1 so much. I don't know. This is a tough question here. Definitely IQR goes down there. Even if I remove the outliers, that one and that one, I've still got, now this is my median, there's my Q1, there's my Q3. So in this one, you're right, the IQR didn't change by removing the outliers. So I guess you're right. IQR would stay about the same. Okay, we've got about 4 minutes left. Calculate the following, I can't read that. For the new data set, the one without the outliers. All right. So if we take this data set and we remove those, we just have 4 14s and 4 15s. So what is the mean? I'm sorry, we have 4 14s and 5 15s. So let's see, 4 times 14 is 56, 5 times 15 is 75, so we have 131 divided by 9 is the mean. What's that number? 131 divided by 9.
You said 14.5, right?
Well,
for me.
it's 131 divided by 9. What's that on your calculator? We're getting...
14.5.
Is it exactly? I don't think so.
Well, it's 14.55555.
Okay. Okay. And we don't do... Does she have you round off to... So x is 14.55 continuous. Okay. We still don't know how to get the standard deviation, but we can get Q1.
I'm sorry, but I have to get ready for church.
Oh, that's
so
fine.
I have to go.
That's fine. Yeah, it's almost 10 o'clock anyway. So that's good. Okay.
Well, thank you.
We'll talk to you next time, Marina. Bye-bye.
Okay, thank you. Bye.